Okay, I want to look at problem 10 from our review activity now. And in problem 10, we're looking at a particle that's sitting in a vertical exhaust duct. So here's a particle, and there is some sort of upward gas flow in this duct. And we want that upward gas flow then to balance out the terminal settling velocity, the effect of gravity on the particle within this duct. The question asks, which particle size is too large to be carried out of the duct? So the larger the particle, the faster its terminal settling velocity, and so the threshold size will kind of be given by this point at which the terminal settling velocity of the particle equals the gas velocity. So if the terminal settling velocity is greater than that gas velocity, the particle settles out. So we get our threshold size by this equality up here. So we are given a volumetric flow rate, and we have to calculate the velocity of the gas from that volumetric flow rate divided by the cross-sectional area of the duct. So we have a volumetric flow rate of 0.1 cubic meters per second, and this is a circular duct with a diameter, of 60 centimeters. And so from that ratio, we get a gas velocity of 0.3536 meters per second. Now we can, for the time being, assume the Stokes regime. And if we do that, then our expression for the terminal settling velocity is the particle density times its diameter squared, gravitational acceleration, the Cunningham correction factor, our fluid viscosity, and our dynamic shape factor. So just to be thorough, we can say we're going to assume that these are spherical and that the Cunningham correction factor is 1. Then we're looking for the particle size, right? So dP should be this velocity of our gas, which is also our terminal settling velocity, times 18 times the viscosity of our fluid. We're looking at air at standard conditions. Then we're going to divide that by the the density of our particles, which is given as 4,000 kilograms per cubic meter, and gravity. And all of this then is to the 1/2. Now if we plug those values in, we get a particle size that's around 53.9 microns. So any particle that has a size greater than 53.9 microns will have a larger settling velocity and not be captured in the duct. For completion's sake, right, we assume that this is the Stokes regime. We should technically go back and calculate our Reynolds number as the density of the gas, the length scale of our obstruction, some kind of velocity, and the viscosity of the gas. So we're looking at air. We just calculated a size of 53 microns. And we have a fluid velocity of 0.35 meters per second. Divide that by the viscosity of air at standard conditions. I should have written kilograms per cubic meter up here. And then we get a Reynolds number that's about 1.27. So it's borderline, but we should be okay to assume Stokes.